A voltage-voltage feedback amplifier circuit is discussed in this video. This circuit is implemented in two stages of NPN BJT or bipolar junction transistors as shown. And at the input we have a small signal AC input Vs A sine omega t with Rs input impedance, the signal impedance, which is 200 ohm, and then Vs itself is A sine omega t. A is a small amplitude like 1 millivolt or so, or even less, and omega is the frequency of interest. So this is applied at the input of the circuit, and then at the output, V out is a sinusoid with the same frequency but amplified magnitude or amplitude. We want to find the voltage gain of this feedback amplifier V out over Vs, which we refer to as AVF, in the presence of feedback. Also, we want to find the AC input impedance Rin as observed from perspective of this point at input, and we want to find the R out or output AC impedance with feedback as observed from perspective of output. To achieve this, I'm going to go through three steps. Step one, I'm going to follow the feedback in this circuit. So I'm going to follow the feedback so that I investigate what type of feedback I have. Is it a negative feedback? And I'm going to show it's a voltage, basically sample the output voltage, apply the sort of a fraction of that sampled output voltage in series with input. So I'm going to show that. Then after that, I need to do the DC bias point for the BJT computation so that I find the operation point, and therefore I find the collector current of these transistor T1 and also transistor T2, the DC collector currents, so that then I can use them for AC analysis. Okay, and finally, after doing that, I would do the AC equivalent circuit. I'm going to show the AC equivalent circuit and how we can find the values of these parameters or questions for this feedback amplifier. Okay, so first, follow the feedback. This one. Look at the input. Let's say Vs is increasing. Basically, this node is increasing. This is a decoupling cap, so it's short at the frequency of interest. Therefore, if this node is increasing voltage-wise, so voltage here is increasing, the voltage of base of transistor 1 is increasing as well. So this node is voltage-wise is increasing. That means the voltage of base emitter of this transistor 1 is also increasing. We know the Shockley-PN junction equation clearly indicates that the IV equation for the PN junction of the NPN transistor looks like this. The collector current, so IC equal to the saturation current of the PN junction, e to the voltage of base emitter divided by the VT, which is the thermal voltage, which is roughly 25 millivolt, assuming the junction of the NPN transistors is at room temperature. Okay, so when the numerator of exponent VBE is increasing, naturally the collector current is increasing. So IC1 start going up as well. If the IC1 is increasing, that means more voltage drop across RC1. Therefore, from a fixed 12 volt supply, we are basically going away at the collector. So voltage of collector of transistor 1 is decreasing. This is another decoupling cap. So it's going to be shorted, so then AC-wise at the frequency of interest, which means this collector AC-wise is shorted to this base of transistor 2 AC-wise. So VC1 going down, VB2 is also going down. That means notice that the emitter of transistor 2 via this bypass cap, which is shorted at the frequency, at the AC frequency of interest, is connected to ground. So effectively the emitter of transistor 2 is AC-wise grounded, so at 0. Therefore, for the voltage of base emitter of transistor 2, if the base voltage is dropping, the VBE is dropping as well. So VB2 dropping, VBE dropping, and again going back to the Shockley-PN junction equation for the bipolar junction transistor, we have VBE dropping the exponent, therefore I collector dropping exponentially. So IC2 starts dropping. That means less drop voltage-wise across RC2, and we are connected to the 12 volt fixed supply. So when we have less drop across RC2, it means the voltage of collector, which is AC-wise shorted via this shorted cap to V out, it means V out is increasing. So it's actually a good sign because we started with Vs and VB1 going up, which means the base of this transistor going up. At the same time, that resulted V out to go up, which then, if you look at this feedback system we have here, the combination of series of RA and RB effectively. So V out is sampled by this wire, and then at this node here, a fraction of that sample, which is roughly RB over RA plus RB times V out, which is roughly effectively 0.1K divided by 5.7, so 1 over 57 V out. A fraction of the output voltage appears here, and please note that AC-wise we are shorting RE1 via this bypass cap that is shorted at the AC frequency, so from AC perspective RE1 doesn't exist. AC-wise emitter is connected directly to this point, so what it means, this fraction of the output voltage appears at the emitter of transistor T1 AC-wise. And when V out is going up, this fraction is also going up. So effectively, circuit tries to follow. We started with base of transistor 1 going up. Now we see that the circuit is trying to also increase the emitter of transistor 1 as well. So it's chasing the base, trying to counteract the increase so that it basically tries to keep the base emitter constant. So it's a negative feedback. So we confirmed how the circuit is working big picture wise, and we confirm it's a negative feedback and it's sampling the output voltage, and it is applying a fraction of that as feedback to the emitter and sort of subtracting from the base. So it's a sampled voltage at the output and then subtracted from the input voltage in a series format. So it's a voltage series feedback. Okay, now that we understand that, let's move on to DC bias analysis quickly for these transistors so that I can find the operating point and then the AC parameters that I need for the AC analysis. So let's start with transistor, let's say, so I'm going to start with T1. So let's say BJT, so BJT T1, this transistor here. So DC bias analysis, DC bias. Okay, first to start with the R1, R2 in series effectively, I'm going to make the assumption that the DC current of the base of transistor 1 will be small, but we have to check it. So effectively, if that is true, R1, R2 are in series, and I can find the voltage of base of transistor 1 DC wise. So voltage of base of transistor 1 DC is equal to VCC supply, and it's a voltage division between R1 and R2, so it's going to be R2 divided by R1 plus R2. So we're talking about 12 volt times 20 kilo ohm, and the sum of the 20 and 60, which is 80 kilo ohm. So it's effectively just 1/4 of 12. So the base of transistor 1 is at 3 volt roughly. Okay. So as a result, what I can say is the emitter of transistor 1 is V base minus 0.7 DC bias, so it's going to be 2.3 volt. That's the voltage of emitter. DC wise, we have the series of RE1 and RB. The reason I can neglect the impact of RA is because RA, as you can see, is 5.6 kilo ohm in this circuit. And that is not all. I mean, from perspective of looking at it this way, there is also a RC2 and there. So it's a large resistor we are looking at. So what I'm trying to say is this 0.1 kilo ohm, when we look from perspective of this emitter downward, this resistor is much, much smaller than whatever we see in parallel with it. So I'm going to neglect these large one. And I can make the assumption that for DC analysis, RE1 and RB are effectively in series. So therefore, what I can say is, I can say the current of, let's say, collector of transistor 1 DC is roughly equal to the current of emitter, given that we make the assumption these are transistors with beta at least 100 or 200. Let's go with 100. The current gain of transistors. So I'm going to make the assumption collector and emitter roughly the same because of large beta. And the current of emitter obviously is the voltage of emitter of transistor 1 divided by the series of RE1 and RB. So it will be RE1 plus RB, which is 2.3 volt divided by then 4.4 volt. So if we compute this, it turns out to be on the order of 520 microamp or 0.52 milliamp. So that's the collector current and emitter current of transistor 1. As a result of this, what I can say is I can say the base current of transistor 1 is going to be, let me put it here. So the base current of transistor 1, which is the collector current divided by beta, is therefore on the order of roughly, say, 5.2 microamp. Very small, 1/100th less than collector current. So it was a valid assumption because take a look at 12 volt divided by 80K. 12 divided by 80K, you're talking about a large number. So you're talking, compared to this, so you're talking about, say, 150 microamp. So the current that is DC current that is going this way is 150 microamp, and that's pretty large compared to the base current. So neglecting base current is a good approximation, practically speaking. We can continue that. So, all right, what I have is 5.2 amp, and what is the important thing about this? Well, the effective impedance observed from AC impedance observed for the base emitter of transistor T1 as observed from base is referred to as HIE of transistor 1, or sometimes people say RB1, is equal to just the thermal voltage divided by the voltage, the current of the base of transistor. So it's 25 millivolt. Again, assuming the PN junction of this transistor is roughly at room temperature for the 25 millivolt thermal voltage, divided by the current of the base, 5.2 microamp. So that will give us roughly 4.23 kilo ohm for the RB1 HIE1. So that's the AC parameter that I wanted to have. Okay, so that's one thing. Let's do the same thing for transistor T2 for, again, DC bias of the second stage, transistor T2, same idea. Voltage of base of transistor 2, as you can see, it's again, we make the assumption that the base, let's say, the base current DC of transistor 2 is going to be negligible compared to this current that is going through the series of R3 and R4. So IR3, let's say. So then then R3 and R4 are effectively in series, and then I can simply find the voltage of base of transistor 2 by just the voltage division between these two resistors. So it will be, again, same idea, is equal to VCC, or the supply voltage, times R4 divided by R4 divided by R3 plus R4. And it turned out to be 12 times 15K divided by 35K, because the other one is 20K. And that will turn out to be on the order of 5.14. So 5.14 volt. This is the base voltage, and emitter voltage is 0.7 volt below the base naturally. So I can say voltage of emitter of transistor 2, BJT transistor 2, is this number minus 0.7, which will give us 4.44 volt. So same idea now. We have DC-wise, we have the DC voltage across RE2. We can find the RE2 or RC2 as well. So I can say, therefore, IC of transistor 2 DC is equal to, roughly, because of the large beta, IE2, which is the voltage of emitter of transistor 2 divided by RE2. In this case, we're talking about 4.44 volt divided by RE2 is 4.3K. So it will be 4.3K, which give us a collector current, emitter collector current roughly on the order of 1.03 milliamp. So the benefit is then the DC current of the base of transistor 2, which is the collector divided by beta of the transistor, roughly turn out to be on the order of 10 microamp, which is again small. So the assumption we made that we just considered these two resistors in series neglecting the impact of IB2 is a valid one, because this current is much larger than the IB2 DC-wise. Okay, so with that, then I can say the AC analysis for the AC parameter of transistor, hybrid parameter Hi2 is what is referred to as RB2 is equal to the thermal voltage divided by the DC current of the base, which is then 25 millivolt divided by, in this case, 1.03 milliamp, and that will give us the RB2 or HIE2 for the second BJT transistor on the roughly 2.5 kilo ohm. Just to make sure I'm not missing something, sorry, 25 kilo ohm. So we found, my bad. So I just jumped, it's 10 microamp, so I need to put 10 microamp here and it's 2.5 kilo ohm. Okay, so 10 microamp for IB2, which we found it. Okay, 2.5 kilo ohm. So that's the HIE and RB2. Therefore, we found the voltages. Maybe the last thing I need to do is just to sanity check the collector voltages of these transistors. Of course, since we have the collector emitter current, for example, in this case, we have 10 kilo ohm here, RC1. So I can naturally say the voltage DC of collector 1, so DC voltage of collector 1 for the first transistor is the VCC supply minus the voltage drop across the RC1, which then turn out to be, this guy is 12 volt, and of course this one is half a milliamp times 10K, and roughly it will turn out to be 6.8 volt. So 6.8 volt for the voltage of collector for transistor 1. And for transistor 2, if we do the same calculation, it will turn out to be VC2 with the same reasoning is roughly on the order of 6.2 volts. So a very good DC bias values for the voltages of the collector of these transistors, especially the 6.2 volt DC here is midway between 12 and the emitter, which is the AC grounded. So it gives us the possibility of the maximum swing if we want. Okay, I mean roughly. We don't need that. Of course, this DC swing and AC swing is different because of the situation we have with the bypass, with the decoupling cap here. Okay, so let's now that we are done with this, let's go ahead with the third step, which is now the AC equivalent circuit. What is the equivalent circuit for this voltage feedback amplifier? So again, we are sampling voltage at the output via this network of feedback or feedback network, and then we applied it back to the input, and we are subtracting the result of it at the emitter from the base, which is the input. So from the perspective of the circuit, what it looks like this circuit. So we have the supply voltage. In this circuit, we have the supply voltage here. So supply voltage, Vs, plus minus AC, and then we have 200, let's say ohm, Rs, and then we have the input AC impedance. So we have, let's say, plus minus Vn. That's before maybe this is stage, I show you first the AC model of the circuit. So we have Vs, we have 200 ohm, and then we have 60K and 20K in parallel grounded, because 12 volt is AC ground. So that would be 60 kilo ohm and then ground, AC ground, and then we have 20 AC ground. This is the point that we are now at the base of transistor 1. So from perspective of feedback network, this is exactly the point that I refer to it as Vn, because then we have the transistor, and at the emitter side, we only see, again, RE1 is bypassed by this bypass cap, we only see RB. So at the emitter, we see only RB, which is grounded. So that's RB, the 100 ohm resistor. And then at the collector of this transistor T1, so this is AC equivalent circuit. So now at the collector of transistor T1, we have RC1 10K connected to AC ground 12 volt. So we have RC1 10K, there you go. So that's 10K, 10 kilo ohm. And then we have these two also AC grounded on one side. So AC ground and of course ground. So we have virtual ground and actual ground. So we have R3 20K and 15K. So I'm going to show it here. We have 20K and we have 15 kilo ohm. And finally, at the base of transistor, the transistor T2, I'm going to just show it here. So at the base of transistor T2, we get to that, and then emitter is AC virtual ground because of this bypass cap. So we have transistor T2 with emitter grounded. Okay, and finally we have the RC2 at the collector of transistor T2, and then this is a decoupling cap shorted effectively AC wise and then connected to 5.6 that goes to the emitter. So we have the 5.6. There you go. We have the 5.6 kilo ohm grounded. And then finally we have this route, 5.6, back to the emitter of transistor 1. And here is the output. This is the AC equivalent circuit. If we want to highlight what's going on, here is the feedback system. So this is our beta, the feedback. So I'm going to show you. This is what we refer to as beta, and this is what we refer to as, let's say, the amplifier itself. So effectively, when we are dealing with feedback amplifiers, this is all the things that will generate Vin for us. So effectively, system looks like this. We have a Vs, we have a bunch of stuff, generates for us the Vn, and Vn goes into a subtractor. So this is basically the base of transistor 1. This is basically the emitter of transistor 1. And here we are at the emitter. So resistor RB is there. And then we have the RA, which is 5.6 kilo ohm. So this is our feedback network, beta. And then we have the open loop amplifier, and it generates the output voltage for us that is now sampled by the feedback network. So we know that from feedback amplifier basics that the overall gain of this portion, so forget about this segment for now that I'm highlighting with a different color. Let me just make sure that the color is there so that it's not forgotten, but at the same time we are careful at what we are considering. This portion that I show it in green, the part that I don't care right now, but I will deal with it later. From perspective of Vn, I have a feedback system. So that's exactly the point Vin I'm showing you here. Here is Vin, and here is Vout. So the total gain of this system, of course, let's put it this way. V out over V in, not Vs, over V in with feedback is equal to A over 1 plus beta A. A is the open loop gain, meaning this guy, and beta is just the fraction that is enforced by the feedback network, not the beta of transistor. Now, if the AV or open loop gain of the system, so this is open loop gain, basically when feedback is not there. If this is large, then basically in numerator denominator, beta AV 0 and AV 0 or AV open, we can consider that if AV open is very, very large, then we can make the assumption that this whole thing is simply AV open divided by beta AV open, because we're going to say this is much larger than 1. And if, let me put it this way, if beta AV open is much larger than 1, then we can say, so this is effectively 1 over beta. So a quick, let's say, rule of thumb or sort of a quick first order analysis of the feedback voltage gain in the system, assuming this is true, which is questionable, of course, might not be exactly true, but assuming that's the case, you can say, okay, beta in this system, as we talked about, it is 1 over 57. So one more time, beta is RB over RA plus RB, a voltage division between these two guys. So it's so that is effectively what the feedback voltage is. So the plus minus VF, the feedback voltage across RB, divided by the output voltage that is sampled. So plus minus V out come here, and plus minus, let's say, feedback voltage comes and arrive at the emitter and subtracts from the input voltage. So therefore, I can say this one is 1 over 57. So now, there you go. Therefore, the V out over V in, the overall system voltage gain for with feedback is 1 over beta, which means 1 over 57, which is 57. So without further calculation, I can say it's 57 gain in this circuit, roughly on that ballpark, but that is just the approximation. Now let's do the actual calculation, and that will be the AC analysis, which we can do it very quickly. So for that purpose, I'm gonna just quickly go through the AC model we have in this circuit. So when we apply V in, I'm gonna remove these guys. Okay, when we apply in the AC model that we just investigated, when we apply V in here, it will generate some input current. So I1, let's say. That's the I base of transistor 1. What is that? I can just compute it easily like this. I can say I, and this is AC analysis, of course. AC, steady state analysis. So I can say I base AC of transistor 1 is the Vin, and Vin is not the source. Again, be careful. Vin is the sort of intermediate voltage we have here that we're going to compute it easy from the source. This circuit is not difficult, the green portion. So Vn divided by whatever input impedance I'm observing from the base of transistor 1. What is that? It is, so I'm going to say R, let's just say what is it. So we're going to have HIE or RB1 basically plus whatever resistor seen like here, AC wise. But fact is we have RB 100 ohm, and then we have a very large resistor, whatever it is, 5.6 series with something in parallel with RB. So we can neglect it because it is much, much larger than in parallel with 100 ohm. So it's roughly 100 ohm. But that is a impedance in emitter. If you want to push it up to and reflect it into the base side, then we have to multiply it because the base current is 1 over HFE plus 1 of the emitter. We have to multiply with beta or HFE plus 1, and HFE, as I said, is 100. times the RB, the 100 ohm. So basically we have Vn divided by this resistor we have. So we refer to this as, let's say, R, just to avoid confusion, let's refer to this as R in 1 or R in. This is not really the input impedance, because input impedance needs to be computed from this node. What we are doing is we are looking from this node. So it's a little bit different, and I'm worried about that confusion. So let's name this as Rx. Okay. All right, then, this Rx is what? This Rx is, we computed this. This is the value I computed here, 4.23 kilo ohm. So I'm going to just substitute it there. 4.23 kilo ohm plus this one is 101 and times RB, which is 100 ohm. So that would be 0.1 K. So in summary, this Rx is simply on the order of, say, 14. Okay, so it's on the order of, say, 14.24 or 25. Say 14.25 K. Okay, so we have this voltage, and then let me just make sure I'm not missing something, because there are too many numbers here. 14.30. So let's say 14.30 kilo ohm. Okay, so that's the value of Rx for us, as observed from perspective of the base of the transistor 1. Okay, so I'm going to just put it here, 14.3 kilo ohm. That defines the AC current IB1. But the nice thing is, if you take a look at, the way transistor work, when we have IB1, then we have roughly the HFE times that, which means we have 100 times IB1 as IC1. Now, that current, we only care about the portion of it that goes through the T2. So what we get is this current here, which is IB2. To find it, we just need to consider these three resistors and the effective resistor we are observing from perspective of the base, which is RB2, so which is 2.5K. So it's a current division, basically. We have 100 IB1 and a current division between these guys and the base of transistor T2 with just 2.5 kilo ohm. So I'm going to just show it. From perspective of here, we have 2.5 kilo ohm RB2. So that shows again why we needed to do the DC bias analysis, not only for sanity check, but also finding these input impedances, HIE, hybrid impedances of the transistors. So then what I can say is, I can say I base of transistor 2 is we have the 10K in parallel with 20K in parallel with 15K. So that's the parallel of these three resistors. And then divide by 10K, 20K, 15K, and plus the HIE2, which is 2.5K. That's the current division. So I just did a current division. And then times, of course, times 100 IB1. So that's what I needed to do. And for that, we end up finding the value to be roughly on the order of, let me just make sure I'm not missing something. So we have 15 and then we have 20 and then, okay, so what we get is roughly on the order of 15, 20, and then 10. So it will be 86 divided by 18.6. So we get about 4.6 for this guy. This guy is roughly 4.6, I think so, on that order. So 4.6 kilo ohm. So 4.6 kilo ohm here as well. And then therefore the ratio here that we are calculating becomes 4.6 divided by 7.1. So it's about 0.65 times 100. So this really just turned out to be just 65 times IB1. That's IB2. Okay, but this IB2 with the direction we found result in a current that goes this way. So because of the way it is, it's coming out of the base, basically reducing the base. So it goes this way as well. So this become IC2, which is 100 times IB2. But that can only go through the combination of whatever resistor we are seeing this way. So it's 5.6K in parallel with whatever we are seeing this way. And this way we see a 5.6K, and then we have in series, we neglect the resistor. The resistor here is, let's say, not, is little. So we effectively have just 100 or less. So what I can say is effectively I just have 5.6K, practically speaking, in parallel with 5.6K. So therefore the collector, let's say, effective resistor or impedance as observed this way is 5.6K parallel with roughly 5.6K. This current IC2 we found is flowing through this effective impedance this way. So it causes a positive voltage. Therefore, I can say voltage of output is AC-wise is equal to the 100 IB2, the current of the collector for the second transistor, times the 5.6K parallel with 5.6K, which is 2.8K. So what we get is, therefore, as a result of this analysis, we get, this is, just to make sure I'm not missing something. Okay, and I'm going to substitute for IB2 from here, right? So this is equation, let's say 1. This is equation 2. I'm going to use equation 2 to substitute for IB2 by saying it's 65 times IB1. So I'm going to get 100 times 65 IB1 times 2.8K, which is the result of these guys. So, and then IB1, I'm going to use equation 1. In equation 1, I found IB1 is a function of Vn. So now I'm going to use equation 1. This is equation 2 that I use here. And it becomes 6500. IB1 is Vn divided by 14.3 kilo ohm. And then here we have 2.8 kilo ohm. So if we simplify this whole thing, we get 6500 times 2.8 divided by 14.3, which give us 1270, roughly 3. So let's say 1270 roughly. So it roughly 1270 Vn. We found it. We were chasing V out, and we found it's 1270 Vn with this is open loop, right? We're talking about this voltage, AV out, AV open loop. So therefore, I can say AV open loop, which is V out over Vn, is when the loop is open, of course. When the loop is open, is equal to 1270. I mean, that sort of solidify what we were looking for. We said check in the previous analysis, we said AV feedback, which is V out over this V in with feedback. So this was open loop, this is closed loop basically. So closed loop. We said it's AV open loop divided by 1 plus beta AV open loop. And then we said, if this guy is much larger than 1, we are safely saying is 1 over beta. But now let's do it accurately. So 1270 divided by 1 plus 1 over 57 for beta times 1270. So this guy turned out to be on the order of, say, 22. So this value here is about 22. 22.3. So it's not exactly much larger than 1, but practically speaking is good enough. I mean, if we now calculate it accurately, we end up finding this whole thing to be equal to, let me just make sure I'm not missing something. So it's going to be 1270 divided by 23.3, so 54.5. So open loop gain is approximately 54.5 volt over volt. So not bad. I mean, previously we said without further AC analysis, it's estimated to be 1 over beta or 57. Now we find it more accurately to be 54.5. Okay, now the only final step that I need to do now that we found the closed loop and open loop gain would be just the feedback. Now, this is, by the way, V out over V. And if we want to find, let's say, V out over, let me change the color so that it's clear. If we want to find V out over Vs with feedback, right? So in this case, I can say it's V out over Vn times Vn over Vs. This one is the one we just found to be 54.5. So this one is 54.5. And then we have Vin over Vs, which is simple voltage division between, basically we are dealing with the green network shown here. So we want to find Vin over Vs, which is simple voltage division now. It is now a consideration of the Rx as we found in parallel with, say, 20 and 60K, and then voltage division with 200. And 200 is small enough so that we can say effectively Vs appears at Vin practically. So I expect Vin over Vs to be close to 1, but let's do it then. So it's going to be times Vin over Vs is going to be just 20 and 60 in parallel, and then parallel with the value of Rx that we found, 14.3K. So it will be 20 parallel with 60K kilo ohm, parallel with 14.3, this is Rx, kilo ohm, divide by this whole thing, 20K, 60K, Rx, and then plus 0.2K Rs. This is roughly 1. We can say it's 1. So effectively in this example is just 54.5, also V out over Vs. So for the input impedance, it's not difficult now because we have, we need to be careful. This calculation I had here for Rx is actually need to be multiplied by 1 plus AV beta, because that is the impedance with the loop, not without the loop. So that's very important. I'm gonna talk about it. I should have mentioned it a little bit earlier than starting this computation here for the impedance. But it's just solidifying that it's really 55.4. We can say V out over Vs is very close to 1 actually. So for the input impedance, what I can say is this. I can say the input impedance in this system is like this. As observed from this point, which is the Rin, what is requested in the circuit, see, Rin, is going to be R1 parallel with 20K, then parallel with input impedance with feedback. So Rin with feedback, or Rx with feedback, let's put it that way. So in this case, it will be Rin is equal to 60K parallel with 20K, parallel with, without feedback, we found that we see Rx here, but that Rx is without feedback. With feedback, as known for the voltage feedback network, it's going to be amplified input impedance. So it will be Rx times 1 plus beta AV open loop. So this guy is 14.3, and this thing, we just found it to be 23 roughly. So 23 times 14.3 give us on the order of 300 kilo ohm. So, and that's pretty large compared to 20K and 660K. So 14.3 times, let's say 23, 330 kilo ohm. So I am just going to make the assumption we are dealing with 20 parallel with 60, which is then about 15K, let's say roughly 14K on that ballpark. So 13K maybe, 14 kilo ohm maybe. So roughly. So input impedance of this circuit is just basically 20 and 60 in parallel. That's it. But the input here is much larger. So with that said, for the output impedance, it's the same idea. So output impedance of this circuit, if you take a look at it without feedback, is just 5.6, and then another 5.6 here, and the R out of the transistor AC wise with emitter in AC ground or virtual ground. So I'm going to show it here. So let me move this away. Okay, so what I'm going to show is from the output of the circuit, I observe RC2 5.6K grounded. So that is my 5.6K. I observed effectively just RA, because RB is negligible, so just RA grounded, 5.6K. And I observed R out, basically R collector emitter of transistor 2, the effective resistor between the collector emitter, and then emitter is AC ground or virtual ground. So RC2. This RCE, RCE2, or let's do the small signal notation, RCE2. So, and this is V out, but this is without yet feedback. So RCE2 is what is just early effect voltage divided by the bias current of transistor 2. Early effect is roughly 250, 255, 200 volt to 250 volt. IC2 is about 1 milliamp as we computed earlier for transistor T2, which I did it here. We found it to be roughly 1 milliamp. So all I'm trying to say is, therefore, considering this thing 250 divided by 1 milliamp, you're talking about RCE2 on the order of 250 kilo ohm, which is pretty large. So I'm going to therefore, practically speaking, I'm going to neglect this guy. So RC2 is too large to be considered for this analysis compared to 5.6. Now, what feedback does in this voltage feedback, contrary to input impedance that it was magnified by 1 plus beta AV, the output impedance with the consideration of feedback is basically output without feedback divided by. So output without feedback divided by 1 plus beta AV. So it will be 5.6 parallel with 5.6. Divide by this one we computed is 23 roughly. So 23. Sorry. So it's going to be just, let me see if I can get rid of this, because okay, finally. So 23. And if we compute this, we're talking about 2.8 kilo ohm divided by 23 roughly, 23.3. So about 120 ohm. So this resulting R out with feedback to be roughly 120 ohm in this circuit. Therefore, in summary, R out is roughly 120 ohm with feedback. R in with feedback, of course, is basically just R1 and R2 in parallel, because The RX with feedback is much large, is 330 kilo ohm. So, and the AV open loop is 1200-ish, 1270. AV closed loop, as we, in a sort of a first, let's say, first round, very rudimentary analysis we found it to be 57, but then detailed analysis showed that it was a good approximation because it's actually 54.5-ish, in that ballpark. Okay, I hope that this detailed analysis, or sort of a tutorial with an example of a voltage or voltage series feedback amplifier involving BJT transistors is helpful in terms of showing how we need to analyze the circuit, how to need to follow the feedback so that we understand what the circuit is doing, how to find a DC bias, let's say quiescent point of the transistors, so that then we can go ahead with the AC analysis in consideration of feedback. I hope this is useful. Thanks for watching.